Good morning and welcome to the second semester of Contactless Organic Chemistry. Chemistry 261 is going to be divided into effectively 3 units. One is going to concern itself primarily with the carbon-oxygen double bond, or the carbonyl group, as chapters 17, 18, 19, and 20 in our text. 17 and 18 are aldehydes and ketones, and 19 and 20 are carboxylic acid and derivatives. That'll be the first unit. Second unit is aromatic chemistry. Things that contain a benzene ring or a heterocycle 6-membered aromatic ring or 5-membered aromatic ring with nitrogen or oxygen in it. And then we'll do a brief kind of bridge to biochemistry where we talk about sugars and peptides and proteins, nucleic acids, and things like that. So we're going to start with carbonyl chemistry, even though in our textbook the aromatic chemistry comes first. Carbonyl chemistry is a little bit more complex. The mechanisms are a little bit more involved, so it makes more sense to start with that because it'll take a little bit longer to grasp all those intricacies. And the logical place to start with carbonyl chemistry is reviewing what we already know about the carbonyl, which hopefully is not nothing. So obviously, you know that the carbonyl group is a carbon-oxygen double bond. Which has, in the case of aldehydes or ketones, hydrogen or carbon attached. So I'm illustrating here with ethanol or acetaldehyde. The AL ending indicating that it's an aldehyde. H prefix indicating that there are 2 carbons. So ethanol is the IUPAC name, but acetaldehyde is the most common name for this. Obviously, you know that the carbonyl group's chemistry is dominated by the fact that it's a polar bond with a partial positive on the carbon and a partial negative on the oxygen, which we can either illustrate with these partial charges, the lowercase delta, or with an arrow showing the dipole with positive end on carbon, negative end on oxygen, and this is consistent with the minor contributor to the resonance hybrid that actually leaves an unfilled octet and a formal positive charge on carbon and 3 lone pairs and a negative formal charge on oxygen. Great rule of organic chemistry number 1 is that if you're unsure as to the reactivity of the species, you can often get some idea of its reactivity by drawing and looking at the minor resonance contributor. So even though this is a very minor resonance contributor with the unfilled octet on carbon, it does explain the fact that the carbon is a position where nucleophiles can attack, and the oxygen is the place where electrophiles can be attacked. And the order in which this happens, whether the electrophile is attacked first by the oxygen to generate a positively charged intermediate, or whether the nucleophile attacks first to generate a negatively charged intermediate, depends on the nature of the electrophile or nucleophile. The other thing you'll probably remember is that the pKa of these hydrogens is significantly more acidic than an ordinary sp3 carbon-hydrogen bond, where the aldehyde and ketone pKa is somewhere between 20 and 22, depending on what else is attached. So the other chemistry that the carbonyl group can undergo is an acid-base reaction that causes the alpha carbon. This is the alpha carbon, the one that's adjacent to the carbonyl group. Chemistry occurs at the alpha carbon because of the acidity of that hydrogen. That'll be the subject of chapter 18, and chapter 18 is arguably the most important chapter in the second semester course, which deals with enols and enolates. But for now, in chapter 17, we're mostly going to be concerned with reactions that either have a strongly basic nucleophile attacking the carbonyl carbon to begin, or an electrophile, often hydrogen ion from catalytic acid, being attacked by the carbonyl oxygen to generate a positively charged carbon that can then be attacked by a variety of nucleophiles. So you should remember this. You should also remember that in the proton NMR, the hydrogen of the aldehyde has a chemical shift of approximately 9 to 10 ppm. And the carbon of the aldehyde in the carbon NMR has a chemical shift around 210 to 220 ppm. So both the carbonyl carbon and the aldehyde hydrogen are distinctive. You probably remember that in the IR, the carbon oxygen double bond of an aldehyde or a ketone occurs somewhere between 1710 to 1720 reciprocal centimeters, and that's distinct from an ester. The ester carbonyl typically higher in the 1730 to 1750 range, so we can often distinguish the aldehyde ketone from the carboxylic acids and the esters. The carbon-hydrogen stretch on the aldehyde is at about 2,800 reciprocal centimeter, plus or minus about 50, and that is lower on the scale than the typical sp3 carbon-hydrogen stretch, which is normally between around 2,900 and 2,950, or just below 3,000. Right? So the carbon-hydrogen stretch can be determined, so you can determine whether it's an aldehyde or a ketone by looking at that 2,800 range, and the carbon-oxygen double bond stretch is very strong because there's a large dipole moment change upon stretching. So you should know some spectroscopy, you should know some acid-base chemistry, and you should remember three, hopefully this is review, you should remember three different ways of preparing aldehydes and ketones. From other functional groups that we talked about in the first semester course. So you should remember a way of converting alcohols to aldehydes and ketones. And you should remember a way of converting alkenes, aldehydes and ketones. You should remember a way of converting alkynes to aldehydes and ketones. Alcohols are converted to aldehydes and ketones. That's an oxidation reaction. And there were a variety of mostly chromium-6 reagents for that, including ECC and DEC and potassium dichromate. Alkenes to aldehydes and ketones was ozonolysis, which is an oxidative cleavage reaction. And then alkynes can be converted to aldehydes or ketones by hydration. And that hydration can occur with either Markovnikov regiochemistry, which would lead to a ketone product, or anti-Markovnikov regiochemistry, which would lead to the aldehyde product. So we're going to review these in turn, and then there are additional ways of preparing aldehydes and ketones that are unique to the aromatic ring. So we're going to be talking about another method, not review, involving electrophilic aromatic substitution. That up here separately. This is new. And electrophilic aromatic substitution will convert an aromatic ring to an aldehyde or ketone. And in addition, there are some new oxidation methods out that the position adjacent to the aromatic ring, which is referred to as a benzylic position, so the carbon here in methylbenzene, this carbon is the benzylic position. And some of these reactions that are useful for positions adjacent to the aromatic ring are also useful for allylic systems, where we have position adjacent to just an ordinary carbon-carbon pi bond. So this is an allylic position, and this is a benzylic position, and those are easier to oxidize. So an allylic alcohol, for example, is easier to oxidize than just an ordinary, in this case it would be a secondary alcohol. So let's start with reviewing the things we already know, and then we'll move into review methods. And you have actually seen an example of electrophilic aromatic substitution, because in the first semester course, before I introduced chapter 6, I did go through an example of each of the major mechanistic classes of reaction, one of which is electrophilic aromatic substitution. And I believe I showed you a Friedel-Crafts reaction as an example. So the first thing is to review oxidation of alcohols with chromium-6 reagents. And the reagents are potassium dichromate, generally done in aqueous sulfuric acid. And that's useful for converting a secondary alcohol so in this case 2-propanol or isopropanol and 2-propanol can be converted to acetone or to propanone. By oxidation with aqueous potassium dichromate and sulfuric acid. And you may remember that this same set of reagents applied to a primary alcohol will actually cause over-oxidation. So if we were to take 1-propanol or N-propanol for normal propanol and use the same set of conditions, we would end up with propanoic acid. Or propionic acid if you want to use the common name. And we say that's over-oxidation. We oxidize it further than we want it to. We're trying to just remove these 2 hydrogens to generate the aldehyde, but we end up inserting an oxygen as well. And you may remember that potassium dichromate reacts with sulfuric acid, so form chromic acid, H2CrO4, which is kind of the chromium analog of sulfuric acid. And that chromic acid reacts with the alcohol to form a chromate ester. by elimination of the elements of water. So we would take out the elements of water, form a chromate ester in a reversible process. And then from this chromate ester, we do an E2 elimination. Remove the hydrogen, generate the carbon-oxygen double bond, and convert the chromium-6 species into a chromium-4 species, and eventually into chromium-3, aqueous chromium-3 plus, which is a green solution. So the orange solution of chromic acid will turn green as the reaction proceeds. So this is an E2 elimination, this last step. Regenerating the acid. Producing the carbon-oxygen double bond. And generating a chromium species. That will eventually decompose further to become chromium-3 plus. And the mechanism by which the chromic acid reacts with the alcohol to form the chromate ester is a 6-step acid-catalyzed esterification reaction known as the Fischer esterification, which we will cover in more detail in a later chapter when we get into carboxylic acids. So, if you want to convert a secondary alcohol to a ketone, this is an excellent way to do it. But if you want to convert a primary alcohol to an aldehyde, this aqueous acidic chromium-6 will not accomplish that goal because of over-oxidation. So to successfully convert the primary alcohol to an aldehyde, I stopped there. You need to use a non-aqueous system. And we need conditions that are closer to neutral. And we'll talk a little bit about why that's true later. So if we're taking a primary alcohol, say cyclohexane methanol, and the corresponding cyclohexane carbonyl, we would need to use PCC or PPC. And a common solvent for these non-aqueous systems is dichloromethane. PPC is pyridinium dichromate. So it's very closely related to the potassium dichromate, except that now we render it soluble in organics by changing the counter ion from potassium to pyridinium ion. Dichromate ion is still Cr2O7. That allows us to do this under non-aqueous conditions. And because the pyridinium ion is mildly acidic and the dichromate ion is effectively non-basic, because the dichromic acid is a strong acid, this is under relatively neutral conditions. And in PCC, you know, stands for pyridinium chlorochromate. pyridinium chlorochromate is a complex of the pyridinium ion, same pyridinium ion that we used in PVC, with chromic anhydride or chromium trioxide, and the chloride ion. So the important piece of the reagent in this case is this CrO3, the chromic anhydride. And that is a heavily positively polarized chromium that's subject to attack by the oxidant of the alcohol. So we will generate a chromate ester, but we will generate a chromate ester through a slightly different mechanism. Because here we have a nucleophilic reagent attacking kind of a neutral chromium species rather than a positively charged chromium species. We do a couple of proton transfers to get this hydrogen from here to there, and we're back to the chromate ester, and then we do the E2 elimination. So the key to this is non-aqueous and neutral conditions. So that's the oxidation of primary alcohols to aldehydes and secondary alcohols to ketones using chromium-6 reagents. With that, I'm going to stop this video so they don't get too long, and we'll pick up the next video with the oxidative cleavage of alkenes.